Hello, this is mathjazz from Almost Cool. This is the second video in our series of videos on derivatives. Our topic today is the power rule. While being one of the simpler of our derivative rules, the power rule is seemingly a point of difference between limits and derivatives. Notice the difference between our limit law and the power rule. The limit law says that if we take f and raise it to the nth power and then take the limit as x goes to a, we get the same value as if we took the limit as x goes to a of f of x and then raised it to the nth power. The power rule, on the other hand, says that the derivative of x to the nth power is n times x to the n minus 1. We can think of our derivative rules as being deviations from what would be nice consequences. What I mean by that is it would be very nice, for example, if the derivative of x to the n were the derivative of x raised to the nth power. It is not true, but that would be nice. It would make calculations easier. It isn't that our derivative rules aren't nice. They're nice in that they let us get the right answer, and they're not exceptionally hard to compute. But what is interesting, or what is needed to be noted, is that the true derivative rules are not as nice as fake derivative rules. Like, for example, the derivative of f times g is not the same as the derivative of f times the derivative of g, which we'll get to in another video. But all of these derivative rules, what we should think of is these are the correct ways to do problems that look like they should be easy, but are not actually as easy as they appear. As we look at the proof of the power rule, we will see why x to the n does not have the same derivative as, that is, the derivative of x to the n is not the same as the derivative of x raised to the nth power. So, and the reason this is because the numerator in the fraction in the definition of derivative interacts with the power n. We remember from our video on the definition of derivative that exponentiation is not a linear process. And that's exactly what's going to happen here, is that this power n is not going to spread linearly over the difference in the numerator of the fraction of the definition of the derivative. Here is the proof. The derivative of x to the n is equal to the limit as h goes to 0 of the quantity x plus h to the nth power minus x to the n, all divided by h. We use the binomial theorem to expand the x plus h to the n product. And in doing so, we notice that there is a positive x to the n in this product that will cancel with the negative x to the n in the numerator of this fraction. After doing that, we notice that there is an h in each of the terms of the numerator, and that h can cancel with the h in the denominator of the fraction. After doing this, we have the limit as h goes to 0 of n times x to the n minus 1 plus alpha h times x to the n minus 2 plus and so on, where alpha is going to represent the coefficient we get from the general binomial theorem. And for each of the terms after this x to the n minus 2 term, there will be some term generated by the binomial theorem, some constant multiple generated by the binomial theorem, and a power of h. So as we let h go to 0, every term except the first one dies, because every term except the first one has an h in it. And this n times x to the n minus 1 is the result that we wanted. It is the right-hand side of the power rule. Thank you for watching this video. My email address is mathjazz9@gmail.com. Feel free to email suggestions on future video topics, to correct errors you found in the video, to ask questions about the material, or for anything else. I hope that you are having a good day, that you are enjoying learning calculus, and again, thanks for watching. Goodbye.